Thank you very much. In this very difficult times and situation, so at least as we have already heard, how your hair looks is maybe not so important anymore for these presentations. We all can relate to this, and yeah, there's more important things. I will talk about cognitive learning analytics and specifically about yeah, the important role of working memory. And this work is performed by our research group here in Tallinn University. Paul Seitlinger, who could unfortunately not join us, postdoc in our project, and Amida Bibi and Nouz, two PhD students, and yeah, I'm leading a research group here on learning analytics and educational innovation. Here is the plan of what I'm going to do. So we'll first talk a little bit about self-directed learning and what role working memory plays. Then I'll introduce the experiment we have run, talk a little bit about the methods, participants, instruments we have employed, experiment results we have gained, and the model-based analysis. And then I will talk just a little bit about cognitive learning analytics and what it could be and how it could enhance learning analytics toolset. So first of all, self-directed learning and working memory. Just to clarify the terms, so yeah, self-directed learning, I have taken not now a very formal definition, but more, let's say, informal description. It is for me basically a way or form of learning where students make the choices about their own learning. They set their own goals, they search for information, they select information to study, and then they learn basically in this way independently. And working memory, yeah, you may have a general understanding of it. So usually, you know, people think of it as this limited capacity store that we have. So you can only remember a certain set of numbers. So if that is the idea of working memory you have, then that is referring to this limited capacity to store some items. But nowadays working memory is understood also in more general sense, namely that it's also very important in the process of actually manipulating the items in your memory. So retrieving, for example, from your long-term memory, retrieving something you have learned before, perceiving, of course, also things from the outside and making sense of them. And then finally also working memory has a very important role of controlling and shielding attention from interference. So it means yeah, that you stay focused, that you are not distracted from other sources of information, for example, and that's often then called executive control. Yes, and why we're talking about working memory in this context is, of course, that there are certain challenges in self-directed learning. So there's quite a number of studies that show that, for example, inquiry-based discovery learning, so those kinds of learning scenarios where students are very active, they are not very often effective also for learning. So especially weaker students do not really benefit. And one of the hypotheses that has been brought up of why that is because this self-directed character of learning puts a high strain on working memory, because the students have to at the same time maintain, manipulate information about the concept they are learning, and at the same time stay focused and make some decisions about their searching. So these two things basically have to happen at the same time, and therefore that puts a lot of strain on working memory, and that's maybe the reason why self-directed learning sometimes is not found to be effective. Yes, so we focus here in this work on, let's say, maybe only a very small part of what self-directed learning could mean. So basically on something we call concept formation. So it means basically exploring a certain topic, certain number of categories, exemplars, and then forming a category that you understand what, for example, a dinosaur, a certain dinosaur category is meaning, and what it's made up of, and what the difference between a certain dinosaurs is to different other ones. This kind of concept formation is studied in cognitive psychology, and in this setting, people basically, or the respondents basically, get the exemplars presented, and then they have to somehow learn them. And we kind of turned this around and came up with a scenario where the students themselves selected those instances, and I will explain it in a minute. And then the first research question is that, do we also find evidence here that working memory capacity in this setting limits the speed in which students learn concepts when they explore those categories by themselves? And then the second question is basically how to support then the lower working memory capacity students in this kind of setting. So that we follow something that we call cognitive learning analytics. So we try to achieve diagnosing students, in this case working memory, or also other cognitive variables based on their learning traces. So this is what learning analytics, as we may know, does. So looking at the learning traces, but we try to map this kind of behavioral factors we see to certain particular cognitive variables, so in this case working memory. And then based on that diagnosis, we try to provide support to the weaker students so that they don't struggle, and that they can keep up and offset basically the negative consequences that there might be. And the way how we do this is through cognitive-computational modeling. So that has the big benefit that we can make precise and computable assumptions on cognitive processes. So we can describe what happens when people are using working memory in these kind of tasks, and we can basically map the traces that we see to those meaningful variables. So basically this is also and you will see we're using neural networks to do this kind of mapping, and so in a sense it's very similar to a machine learning approach that we see in other areas in learning analytics as well. But the difference here is that the parameters that we are learning through our models are not just derived from the data, but they are actually derived from a theoretical model, in this case how working memory works. And so therefore, second question here is, can we use some existing model of working memory to simulate student self-directed search decisions and concept formation, self-directed learning task? So we have taken one model, and the model you can see down here, model by Oberauer and Lewandowski. Can we use this to actually simulate how students are forming concepts? And then we don't want to stop there, but we actually want to, because as I said, we want to diagnose students' individual cognitive constraints. So can we actually use this model also as a measurement instrument, as a diagnosis tool that will then tell us something about individual students? So that is the third research question. Okay, I'll talk a bit about the methods. Firstly, we had basically sample of 105 7th and 8th grade students, local high schools here in Tallinn. They came to the university and basically performed two different tasks. And the first task is related to a measure of working memory capacity. So those people who are knowledgeable about this, they probably know the O-span task, which is usually used to measure working memory capacity. It's a dual task paradigm, and here you can see how it works. So students are presented some letters, and in the end they have to remember which letters were presented. But as a second task, they are intermittently presented with some equations that they have to solve, or basically decide whether 3 plus 2 is equals 8. So they have to press yes or no, and then the next letter is presented, and then again an equation is presented. And then the question how to measure working memory is then how many letters do they actually remember from this dual task paradigm. So that is a validated task and measures how what the capacity of our working memory is. And there's differences in people in how much how that span is and how many letters they can remember hence. So the first one was basically working memory task. The second one then, and this was for us basically later to validate our model. And the second task is a concept formation, search and concept formation task, which we call dinonymy. So nymy is Estonian for name. So find the name for the dinosaur. And we have here in total 8 different categories of dinosaurs, and they are differing in terms of different attributes, different features. So whether, for example, they can't fly or they can fly, whether they are small or whether they are large, and what is their head shape. So do they have a crest or not? And that gives altogether 8 of those categories. So a few of them are shown here. And basically the task of the students is now to learn what these dinosaur categories, how they are called, what the name of these dinosaurs are. And they basically learn it by navigating by themselves through this taxonomy. So they make 3 decisions. Do you want to first see an exemplar that can't fly or can fly, and then they make a choice. Then they make a choice about the second dimension, and then about the third, and then they are presented an exemplar, and then they say, okay, what's the name of that dinosaur? So we can maybe talk later about this task. Of course, you see it is not what we would maybe expect as a now very complex self-directed learning task, but we try to, let's say, take out one important component of what we think is important in self-directed learning, namely that students form concepts about what they are learning through navigating themselves. Okay, and the second important component is then our computational model. I have already talked about it a little bit. So it's basically a neural network, a very simple neural network, a 2-layer neural network. Consists of just 2 layers. So the one is the input layer you see here, layer F. So the network basically encodes all these 3 features that we talked about before. And then the output layer L, which outputs the name of the category, the label, therefore layer L, the linguistic layer. And how this network works is takes the input and basically through this matrix of weights then maps the input to an output pattern. And then tries to select from its memory of previously learned patterns that they have learned. So here you have all the 8 dinosaur categories. Each one of them is characterized by a certain pattern of the output. Then tries to match which is through a pattern matching, which is the best candidate that I should now mention. And then there's 2 parameters that are important here, and which will become later important when we're talking about working memory. The first one is parameter tau, which basically models the interference during retrieval. So it means once the network has outputted a certain pattern, then the pattern matching, so trying to find the best candidate, can be more or less noisy. So if it's more noisy, of course, you'll make more mistakes, and it means that basically you cannot focus really during this retrieval. The second parameter looks more at the learning phase, because Basically, the students then get a feedback when they select a particular category name, and then of course that is wrong or that is right. And by this feedback, yes or no, basically the network adjusts the weights, so to say, unlearns the wrong associations and reinforces the correct associations. That is what's called Hebbian learning. And the second parameter basically determines how well the network unlearns the wrong associations. So again, it is a matter of how well I'm able to focus, let's say, on the really essential characteristics. And for example, how am I able to unlearn misconceptions I have developed, for example, things like that. Okay, so it's yeah, 2 parameters, and then the network basically learns along the students how they are learning and tries to predict what the students are also, what kind of answers the students are giving. Okay, I'll come to the experimental results. We were interested in 2 basic patterns. So the first one on the left side is the search behavior, because yeah, the students could make, as I explained, by themselves decisions on which categories they looked at. And then we were interested in the learning performance. So were they actually learning those names to the dinosaurs or not? And the search, basically we modeled 2 different patterns that we could observe. So the first one looks at what is the probability that a certain category is selected based on how many times the category has been selected previously. And here we see quite a strong positive relationship. So it means if I have selected a category already previously, then the probability of selecting it again is quite high. So it means that the students actually focused their search quite quickly on repeating, looking at certain dinosaur categories. And a similar pattern we see here. So this is looking at in which phase the students are learning. So they went through 7 of those stages, and what's the probability to select a new exemplar from a new category. So of course in the beginning there are no old ones, so everything is new, but then very quickly the students focused in on particular categories. So that's what we see in both of those patterns. And then the learning performance, first graph shows a typical learning curve. So it means it looks at how many errors the students made in selecting the right label, and then over the study phases, of course, this error probability went down because they were actually learning how the dinosaurs were called. And the second one, the second graph we see is looking at the retroactive interference. So it looks at how many intervening cycles there have been, search cycles there have been before revisiting the same category again. So if I revisit the same category of dinosaurs right next to each other, then the error rate is of course very small because there's no interference, there's no retroactive interference. But if there are some cycles in between that I look at other categories in between, then the error rate goes up because then I don't remember certain what I've seen before. Okay, and looking at our main research question then, can we somehow see that working memory capacity has an influence on those? And for this we performed this logistic regression. So the first 2 here are for the search behavior, so predicting PI, so choosing the category and choosing a new category. And you see here that the O-span did not correlate, did not predict the search behavior. So it seems that at least in our study here, working memory did not impact the search behavior of students. So the high and low working memory students were searching basically in a similar way. But if we look at this second result here that looks at the learning curve, then we see that O-span actually had a highly significant effect on this on the learning curves. So it means that, and I can switch to the next one where we maybe see this better. So here you see again the learning curve, and now we have kind of like two extreme groups. So those with low working memory span, those with high, and you see here that the learning curves look similar, but the higher capacity students were lowering their error rates much more quickly. So they were learning more quickly than the lower working memory students. So that has been one of our main assumptions of this work and has been thereby confirmed. And the second research question here was that we can simulate aggregated group data, and yeah, this you can see in those graphs here. So here you can see the data that has actually been measured. That is the white dots and the black dots, the model. So the model was quite accurate in predicting the overall behavior of the students. So these are aggregate measures here, so aggregating over the whole sample of students. But of course, we don't only want to look at the overall sample, but we want to see if we can diagnose individual students' working memory capacity in this case. And then we fitted the whole model basically to each student individually. So in individual learning curves, we try to predict from the actual search behavior of the student. And yeah, it was actually quite successful. So it was possible to predict or to fit this model in 98% of the cases. So only in very few cases it was not possible. And then what you have here is basically kind of like a user model that that tracks each individual students. And now, since the model is based on this computational model, then we can estimate for each student those parameters that I mentioned before and check whether they are correlating with the working memory capacity. So we can see whether these parameters that we estimate, basically just based on their search behavior, whether they have some kind of correspondence to working memory processes. And we see here that yes, in fact, one of the parameters was moderately correlated to the O-span score, and that was the parameter tau, which yeah, controlled this retrieval of the feature labor associations. So we can see that at least in this study, the reason why the lower working memory capacity students were not performing as well was because they had problems in retrieving the previously learned information that they had learned. So it was not the search, and it was also in this case not that they could unlearn the wrongly associated associations, but it was in the retrieval that where the problem was. Okay, so then you could ask probably what this is now all for. Yeah, it is for us an example of cognitive learning analytics. So first we found that basically confirmed what is already, I think, quite well known, that working memory is an important concept, especially if you look at self-directed learning, and when students are when it's expected of students that they explore by themselves concepts in a self-directed way. And through this approach, it is possible now to infer student-specific cognitive abilities, in this case working memory, simply just from their work, from their learning traces. In the future, we want to refine the model, of course, to make the relationship stronger. So at the moment, we don't have very strong relationships, but yeah, I think we can refine the model. And then, of course, we want to then think a little bit about how can we offset those working memory limitations that maybe could apply. So it is then possible to do some kind of personalized scaffolding. So basically diagnosing the students and then offering some help for the particular trouble they are having. So depending on which parameter basically it would be especially responsible for their lower performance, you could think of different ways of how to support it. So for example, display the things they have learned before, or make recommendations about which they should be looking at next, and those kinds of things. Okay, thank you very much. That was all I had to say. Here is all the 4 of us, and if you want to know more, then this is all based on a European project, SATA, and we have put our papers there that you can also read. Thank you very much.